Here's video help for problem 27-10. You know, the calculation that I gave you in the homework written advice, that's a graduate school calculation, and it's kind of tedious, and you can figure it out or you can understand it. But let me give you a much faster derivation based on an undergraduate electromagnetism course. We've got ourselves a cylinder. We'll imagine the cylinder is very long. We're going to get the famous birdcage current distribution. You know, the current that flows along the z direction. It varies along the phi so that it's maximum positive here, maximum negative down there, and then it goes sinusoidally to zero on the edges. And if you actually just kind of look at Ampere's law, you can kind of understand how the field inside is in this direction. And if it's sinusoidal, it's exactly constant magnetic field inside in the x direction. That's wonderful. And that's, of course, the constant magnetic field that we'd love to have for tipping our spins in the transmit coil. Well, for a very long cylinder, we can just look at this on edge and think of it as a two-dimensional problem. Forget about the z direction. And in particular, not only the y and the x, we'll assume we're going to say to ourselves, hey, can we make a constant B field inside here pointing along x? And we'll love to use polar coordinates, r and phi. These are rho and phi in the notes in the sort of the cylindrical coordinates. Let's suppose we want to find a solution that would give us B equals constant in the x direction. Outside, we have a general polar angle solution. You may remember in a general course, maybe even an undergraduate course, that in 3 dimensions you have spherical harmonics. And for 2 dimensions, we just have the harmonic cosine n phi, sine n phi solutions, arbitrary phases and amplitudes for each harmonic, and that's the general solution for the magnetic field away from the sources in a source-free region. We're going to ask now, what is the current distribution? This K is current per unit length, so that if you knew what this density is and you multiply it by a little transverse direction along here, you'll get the current. Ka d phi, this little arc length, will give you the differential current then along Z. What is the K that we need to get that? Well, you know what? We're going to get everything from boundary conditions. We're going to find out the ANs, the phi n's, and the K. They all come from the fact that the normal components of the B are continuous, and the tangential components of the B are discontinuous by any non-zero surface current. Now, by the way, this is, if you look it up, this is K cross the normal unit vector, which is r hat. You'll get that's phi hat. With this is beautiful. It goes so quickly. The normal component is in the r hat. That would be this part. That would be outside. Inside, I just look for the arc component of this constant vector in the x direction. That'll give me a cosine phi. So C cosine phi r hat. Now, that has to equal this part, right at the boundary. But it has to equal it for all phi. That means forget all the higher harmonics. By linear independence, there's nothing to cancel them. They all have to be gone. They all have to be zero, and only the n equal 1 term cancels, and only for phi, the phase equals 0. So that's wonderful. You just have this whole series now is just one term by the boundary condition, continuity and normal, and I've got myself then just a sub 1 term for the whole thing. Now, we're going to get, actually then we even get the A1, because by continuity, A1 then over A squared at the cylinder has to equal this capital C. coefficient of cosine phi on both outside and inside, balance. Now, we're going to figure out what k is. Let's look at the tangential component. The tangential component, is the phi hat. That's now sine phi outside, and inside it's just this tangential component of this x hat, directed constant magnetic field inside. I drew it outside here just to make my little triangle. And that's sine phi, but it's by the way, it's in the minus phi hat direction. Phi hat is a unit vector going that way. So I get c sine phi outside, because see, I was able to calculate A1 in terms of c, minus a minus, because that's actually turning the other way, c sine phi equals mu 0 k. And by the way, if you just look at this and look at this current being maximum up here, you can kind of just see how by the boundary conditions, what the current really has to be. This current is nothing other than 2c over mu 0 sine phi, just from this simple equation. So now I got k, I got my A1, I got everything. So, there's a wonderful theorem, by the way. If you can find a solution satisfying Maxwell's equations and the boundary conditions, you have the unique solution. So, if I say I wanted to find Cx hat, I can do it. It will give me what they call a dipole field outside, corresponding to a surface current with 2c over mu 0 sine phi z hat on the cylinder. But the key is, it depends upon sine phi. It changes with phi. Maximum here, minus maximum here, and 0 on the sides, and sinusoidal in between. And by the way, if I define it in terms of the I0 given in the problem, you can just identify capital C as mu 0 I0 over 2a, k is I0a sine phi z hat, and that's the coefficient of the delta function restricting you to the cylinder. You're done.